Hello everyone. In this video I am going to explain the adder BCD 4-bit BCD parallel adder. Okay, so let's start. So this is your parallel adder. Already I have discussed in my previous video. So in this parallel adder only we'll make it BCD adder. So thing is that while in 4-bit parallel adder, your 4-bit A, that is A0, A1, A2, A3, and 4-bit B, B0, B1, B2, B3 are applied parallelly, and Cin of course for the 4-bit this Cin will be 0, and the carry of the first is propagated to the next full adder, carry 1 of the second full adder goes to the third, and so forth, and S0, S1, S2, S3 are your 4-bit sum output along with the in the round carry C3. Now to make it a BCD, suppose this A and B, A0, A1, A2, A3, B0, B1, B2, B3 are all valid BCD have entered or a given input. But due to the valid BCD, the output may not be valid. Now as you know, the invalid BCD, because BCD means each and every decimal digit in 4-bit binary. Okay. But in 4-bit there are 6 invalid stages. Say from up till 9, 0 through 9 is a valid BCD, and from 9 onwards, that is 10, 11, 12, 13, 14, 15, these 6 numbers are invalid BCD, because these 6 numbers can be represented in 4-bit binary, but in its equivalent decimal it has 2 decimal digits. So these 6 are invalid BCDs. Now to overcome that invalid BCD, what we need to do is we need to add 6 with the invalid BCD. Why is add 6? To overcome the 6 stages of invalid BCD. So now to make it in a circuit, let us see. So this is the parallel adder that we use, where A0, B0, A1, B1, A2, B2, A3, B3 are applied parallelly, Cin minus Cin, which is Cn minus 1, which is 0, and S0, S1, S2, S3 are your output. Now depending on the output, how the circuit can take the decision whether it is a valid or invalid. To see that, let us look at this 4-bit, this S3, S2, S1, S0 along with the in the round carry C3. So up till this 0, 0, 0 through 1, 0, 0, 1, this C3 till now is 0, say. So 1, 0, 0, 1, S3, S2, S1, S0, up till this 1, 0, 0, 1, this is valid BCD because it is 9. Okay, but after that 1, 0, 1, 0 is 10, which is invalid BCD because it has 1 and 0 in decimal. So according to the valid BCD, it is 0, 0, 0, 1, 0, 0, 0, 0, valid BCD. Okay, because in valid BCD means each and every decimal digit in 4-bit binary. Here, although it is a 4-bit 10, 10, but it is 10, the equivalent decimal, it has 1, 0, that means 2 decimal digits. Similarly, say 11, 12, 13, for example, is 13, although it is 4-bit, but it has equivalent decimal digit 1, 3. So each and every decimal digit has to be represented in 4-bit binary to make it valid BCD. So 1, 3, the valid BCD will be 0, 0, 0, 1, 0, 0, 1, 1. Okay, so if you look at up till this 6, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. These 6 are the invalid BCD in 4-bit. So if any one of these occurs at your output here, S0, S1, S2, S3, it has to be added 6, okay, to make it valid. Or if this C3, the end around carry is 1, then also, because if end around carry is 1, then also it is invalid. So because C3 is also our concern, so with the end around carry 1, then again for this 16 different combinations, output is invalid BCD. So in both the cases, we have to add 6 along with the S3, S2, S1, S0. So the condition is if C3 is 1 or S3, S2, S1, S0 is greater than 9. So how to check that? So if we look at that, C3 is 1 is okay, but if we look at this yellow part, you see how to take the decision whether it is valid or invalid in circuit. So it is 1 0 1 0 1 0 1 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. So now if you see the first bit S naught is 0 1 0 1 0 1, every time it changes as like this. So there is if we compare this yellow part with this green part, then if we compare for S naught is, you see here also it is 0 1 0 1 0 1 0 1, like that it is changing. Okay. But in case of S3 is 1 in all the cases, all the invalid cases. S3 is 1 1 1 1 1 1. So all the 6 cases S3 is 1. But here also there are 2 cases invalid BCD where S3 is 1. So we cannot simply say that if S3 is 1 then it is invalid. No, we cannot say that. So S naught also we can't take any decision, because S naught here also in valid case also it is 0 1 0 1, every consecutive number it is changing 0 to 1 1 to 0 0 to 1 1 to 0. Similarly here also the same thing. And S3 also, although it is S3 is 1 1 1 1 for all the 6 invalid stages, but then also I cannot simply say that that if S3 is 1 then it is invalid BCD. No, because invalid also there are 2 cases where S3 is 1. So then we have to check S2 S1. So in case of S2 and S1, you see when S2 is 0, S2 is 1, S2 is 0, S2 is 1, S2 1, S2 0, these are the cases are there. S2 1, S1 1. Okay. Here also it is 0 1 0 1 1 0 1 0 1 1 1 1. So all the cases are there. Then so we base on S2 individually or S1 individually or S3 individually or S0 individually, we cannot take the decision. Then with S2 S1 also together we cannot take the decision whether it is valid or not, because here also S2 S1, if we compare 0 1 1 0 1 1, all the cases here also in this invalid case. So then what is the next option? Next option, we have to take the decision in terms of S3 and S2 S1 or. So you see when S3 is 1, either S2 or S1 is 1 in all the invalid cases. Okay. When S3 is 1, or either S2 or S1 is 1, right. So you see how can we take decision when S3 is 1 and S1 is 1, or when S3 is 1 and S2 is 1, then it is invalid, because you see when S3 is 1 in these 2 cases, both S2 and S1 are 0 0, and the rest in all the previous cases S3 is 0. So therefore for being an invalid BCD, first of all S3 has to be 1, but that is not sufficient condition, but it is necessary condition that S3 has to be 1. Sufficient is S3 1 and either S2 or S1 1, because S3 1 in these 2 cases, both the S2 and S1 are 0 0. Okay. So therefore what we can see, you see in the circuit, this is S3 1 and S2 is 1. If both are 1, then also it is invalid. This is for invalid BCD. Okay. This output of the OR gate, if it is 1, then it is invalid. So if C3 is 1, then it is invalid, because any input to the OR gate is 1. It does not depend on the other input. Output is 1. So if C3 is 1, as I mentioned, C3 is 1, output is 1. So when the output is 1, it is invalid. Now suppose C3 is 0, then also if S3 is 1 and S2 is 1, because the AND gate, both the input 1 means output 1. So if S3 is 1 and S2 is 1, then this output will be 1, and accordingly this output 1, so it is invalid. Or this is OR, because it is OR. So or S3 is 1 and S1 is 1. So that means these conditions, S3 is 1 and S2 is 1, S3 is 1 and S2 is 1, then S3 is 1 and both S2 S1 are 1. So under these conditions, either these or both will be 1, and the output will be 1 here. So output 1 here means it is invalid BCD. So what happen if it is invalid BCD? In case of invalid BCD, we need to H6. So you see, H6, 6 means 0, 1, 1, 0. So 6 means, here 6 means 0, 1, 1, 0. Okay. 6 means here 0, 1, 1, 0. That means here S0, S1, S2, S3, these are all coming in. Along with that, we need to H6. So in the other 4-bit parallel adder, that A inputs A0, A1, A2, A3, this A0, A1, A2, A3. These are directly from S3, S2, S1, S0. Now B input B0, B1, B2, B3 will H6 if invalid or 0 if it is valid. So 6 is fixed 0, 1, 1, 0. So MS bit and LS bit is fixed to 0. So that is why this is 0, this is 0. Okay. Only thing, the middle two are 1 in 6 when it is invalid. So you see, when it is invalid, this output will be 1. So this 1 goes to the middle 2 bit, that is B3, B2 and B1. B2 and B1. Now if it is valid, this 0 or this 1, but both are 0, then output will be 0, means output 0 here is, it is valid BCD. So output 0 means this is 0, this is 0, and these two are already fixed 0. So 0 is added with the S3, S2, S1, S0 here. So it will be the S3, S2, S1, S0 only. So finally it will give you the valid BCD for two valid BCD addition. Okay. So now let's do it in multisim. So in the multisim, this is a multisim. So we'll make that 4-bit parallel adder using this full adder. Okay. So using this full adder, we'll this kind of 4 full adders and one your source, that is binary source, digital source, this type of source. So for B0, B1, B2, B3, A0, A1, A2, A3, and these 4 parallel adder will be used as in my previous video I have mentioned. Okay, let's see how it can be connected. So this is your first full adder, second full adder, third full adder, fourth full adder. So A1, B1, A2, so let me put it as A0, A0, A1, A2, A3, like that. So this is your A0, B0, A1, B1, A2, B2, A3, B3. Okay. So C in is connected to 0. So I'll copy this in and paste this here. Okay, so this is your C in. Okay, C in. So which will be always 0, and this will make it later 0 or 1 according to the given input. Okay. Then these outputs will be connected with the same another parallel adder. So one of the input to the parallel adder will be connected directly to this. Okay. So this is your another parallel 4 parallel full bit single bit full adder. So this sum output is connected directly to the B. Here sum output A. Okay. Then this is to A. This is to A. Same here. The C in. That C out will go as a C in here. C out of this go as C in here. Then C out will go as C in here. Okay. And C in here also, the second also C in is 0. Okay, so this is C in here 0. Now this B input. Now as we see in this case, so B0 input is 0. So this is your B0, B0 also connected to 0. This is already 0. because this scene is 0, the same 0 I can connect here. Okay, and then here B3 is also 0, so this is your B3. So this same B3 also I am connecting to same 0 here. Okay, so this is also 0. Now what I need is 2 AND gate, 2 input and 3 input OR gate. So this is TL AND gate 7408 AND gate 7408. Yes, 7408 AND gate. So I will use this 74 AND gate 1 2. Okay, now let's rotate it 190 degree. Okay, then this also rotate 90 degree. Okay. So where from this 2 will come in? So S3, S2, S3, S1. So this is your S3, S3, this is your S2, and this is your S1. Okay, now we need one OR gate. So 7432, this OR gate, 7432 OR gate. Let's see whether I can make it 3 input or not. No, sorry, this is 2 input only. Okay, we will use 2 OR gate, 7432 1 2. Okay, so I can have this 2 . Okay, so this C3 is connected here, then this is connected here, then okay, then another input is this. Okay, then this will be connected here as well as this will be connected here. Okay, that's all the connection. Then I will connect the output here. Okay, so here I have connected this output probe for displaying the output. So that's all about the circuit. The circuit is done. Now let us check the inputs. Suppose I would like to add 7 plus 5. Okay, so here I'll do it. So if I am going to add 7 plus 5, which is equal to 12 in decimal. Okay, so equivalent in binary, it will be 7 is 0, say 1 1 1, and 5 is your 0 1 0 1. So result is so it will be 0 0 1 0 with carry Okay, suppose I would like to add 7 and 5. 7 and 5 both are decimal BCDs, valid BCD. So 0 1 1 is your valid BCD for 7, 0 1 0 1 is valid BCD for 5. Now as per the normal addition, that means here at this point, so S3, S2, S1, S0 along with this C3, the result will be this 1 plus 1 0, 1 plus 1 0, 1 plus 1 plus 1 1, 1 plus 0 plus 1 1 which carry 0. So at this circuit here S0 will be 0, S1 will be 0, this will be 1, this will be 1 and this C3 will be 0. So now as you see, this 4-bit sum is your 12. So which is an invalid BCD. So to make it valid, what we need to do, you see here SC3 is 0, but S3 and S2 both are 1. So this output will be 1, and because of this output 1, this will be 0, but this is output 1. So output here is 1. So you need to add 6. So therefore, to make it valid, what you have to do is you have to add 6 here. So what will be the 6? 0 1 1 0. So then after this, if you add it up, so it will be 0 plus 0 0, 0 plus 1 1, 1 plus 1 0, 1 plus 1 0 which carry 1. So it will be your 1 0 0 1 0. So that means 0 plus 0 0, this 0 plus 0 is 0, 0 plus 1 is 1, then 1 plus 1 is 0 which carry 1, 1 plus 1 0, 1 plus 1 plus 0 is 0 which carry 1. So now you see this 0 1 1 0, 0 0 1 0 is 2, and here you can put 4 zeros. So 0 0 0 1 is 2 1. So this is 12. That is the valid BCD. So let me put it here. So B3 is let me put A as 7 first. So 0 1 1 so 1. Then B3 5. So 0, B3 0, B2 1, B1 0, then B0 1. Okay. So the result will be, and C0, C in here is C in the first full adder, it is 0. The same C in here also it is 0, and the same 0 is connected for this B input as well, and here as I mentioned, sorry here. Okay, this to B input will be 0, and this will be from that or output of the OR gate. This output of the OR gate. Okay, output of the OR gate. So let's see. So you see, this is yes. So it is C3 1, S3 0, S2 0, S1 1, S0 0. So it is 12. So let me make it 13. So if I make say 7 plus 6, so A is already 7, B is so 0 1, let me put it as 1 0. So 7 plus 6 13. So it will be 1 3. Yes, 1 3. Okay. So it's done. So that is your BCD adder finally. Okay. So this is finally BCD Adder. So now the same I will do it in VHDL. So this is your VHDL in which so click on the file, then new projects, create new project. So here I am putting BCD say Adder. Okay, BCD Adder description, you can write something here. Okay, then next. So this is again for your hardware that has to be connected, because here I am not going to use any hardware, so no need to check anything about this detail about the device. So then next, finish. Okay, so then right click on it, click here, right click on it, and then new source. Okay, so here you need to give the file name for the VHD. So I'll give it as BCD. It should not be the same as that of the project folder, so I'll put underscore BCD Adder. Okay, so it will be a VHDL module. Then next, then you need to give the input output. So inputs here will be, so this is your A is your input, vectored input, so 3 down to 0, that means A3, A2, A1, Y0. Similarly B3, B2, B1, B0. C in is your carry in input, and C out is the carry out, and S is also the output but vectored. Okay, so next, finished. Okay, so this part is done. Then since this BCD adder is having two parallel adders, so first we have to make a parallel adder. Okay, so now we will make a parallel adder as a component. So since we are going to make it a structural, so we will use parallel adder as a structural component here in the BCD adder. So right click on it, then new source, and I will add a parallel adder. So in that parallel adder, so it will be your VHDL module. Next, so here also a this 3 to 0, then B bus 3 to 0, then C in, here also there will be C in, which is single input, then sum say bus 3 to 0, which is your output, and there will be carry out, so let it be C underscore carry out, which is also output, single output. Okay, so this is your parallel adder. Next, finish. So now again this parallel adder also I will make a structural using single bit full adder. Okay, so I will again right click on this parallel adder. You see, on this parallel adder. So because I am going to make this parallel adder as a structural modeling using full adder as a structural component. So now again new source. So now I will put full adder. Full adder. So this is again VHDL module. So next, so here A is your input, B is your input, C is your input, sum, suppose sum is your output, and carry is your output. So here I will put this out, sum out. Okay, so these are all single input, single bit. Okay, so now this is your full adder. So let us first complete this full adder. Okay, this entity full adder. This is the port declaration, entity declaration, then entity declaration in entity ended here, then architecture. The name of the architecture is default is behavioral, let it be same because it is just the name. Of full adder is the entity. Then you need to define the process of your process your A, B, and C. Okay, so the process begin here. Then your sum output is A XOR B XOR C. okay, and carry output is here. Carry output is here, sorry, carry output is here A and B, or B and C, or A and C. Okay, so process ended here in process. Okay, so that's all about the full adder. Sorry, that's all about the full adder. So full adder part is done, so let's just save it. Okay, now this full adder I will use as a structural component, so I will just making it copy so as to make it use of the component declaration in the parallel adder. Okay, so this full adder will be used as a structural component for the parallel adder. So this is your parallel adder. Now here architectural behavioral of the parallel adder is, so before beginning you need to define the component. So component, this full adder is in component. Okay, so the component declaration is done. Now already we have done this parallel adder, so this is the parallel adder that we designed already. Yes, this is your parallel adder. So here what you need to define is this C0, C1, C3, C2 as a signal. Okay, so here you need to define the signal. So signal C0, comma C1, comma C2. So that is also STD logic. Okay, then architecture will begin here. So since there are 4, so I have to define 4 components here. So let it be U1. First you have to put this name of the component, which is full adder. Okay, full adder, port map within brackets. So what will come here? Port map within brackets. So in the first full adder what comes? A0, B0, Cin. Okay, Cin I have given as an input. Okay, so A0, B0. So what will be the A0? This is the A0. So you have to write A within bracket 0, that is A0, comma B0, because it is defined as a vector, so you have to write it like this: A0, B0. Then Cin, how it is given? Cin is directly Cin. So Cin, then sum out. So for the sum out, S, that is also vector, so S0, and carry out. So carry out is C0. Okay, but this C0 is defined as a signal. So C0. So this C0. Okay, so that is your first full adder is defined. Okay. Similarly, the second one, third one, fourth one. Okay, so let it be U2. So port map full adder. So here it will be A1, B1, then it will be C0, then S1, and it will be C1. So it is U2, U3. So it will be your A2, B2, then it will be your C2, C1, then your S2, and this will be your C2. Now in this 4, so it will be your A3, B3, then this will be your C2, then this is your S3, and finally the carry out is your C naught, this C out, carry out. This is your final carry out. Okay. So by this your full adder, I mean the your parallel adder is done. Okay, parallel adder is done. So now let me you see this under this parallel adder, this U1, U2, U3, U4 all are coming. Let's see 0, 1, 2, 3, B 0, 1, 2, 3, C in S naught, C naught. C naught comes here, S1, C1, C1 comes here, S2, C2, C2 comes here, S3, C0 output. Okay. So let me check whether this syntax is correct or not. This syntax is going on for the parallel adder. Syntax is going on. For the first time it is taking longer duration. Yes, it is done successfully. Okay, so let me check the full adder also. Check syntax for the full adder. So for full adder, check syntax is going on. Okay, so this check syntax done for the full adder. Now this parallel adder will be used here in the BCD adder. Okay, so here your architecture behavioral of the BCD adder. So here that you have to declare the component. So this as a parallel adder as a component. Okay, so I'll put it here, parallel adder as a component. So component, you have to type the component here, component parallel adder is so in component. Okay, now along with this, in your parallel adder, in the BCD adder, there are two input AND gate and one 3 input OR gate. So let me define that also. So in the parallel adder, in the BCD adder, so here again I am right click, new source. So OR gate say 3 means 3 input OR gate. So it is also VHDL module. Next, so A, say B, C, and say Y. Y is the output. Okay. Next, finish. So let me finish this OR gate part. Okay. So here architecture body begins. After this, unit define process. Within bracket A comma B comma C, these are the 3 input, then process begin here, then Y is nothing but A or B or C, then end the process, end process. Okay, so that's OR gate part is done. Okay, So that same OR gate will have to define as a component in the main program. So here after this yes, so component OR gate is, then in component. Okay, so OR gate 3 input OR gate is done. Then what we need is one more, that is AND gate. Okay, so now AND gate, which is also your VHDL module. Next, say A is one input, B is one input, and so Y is your output. Okay, next, then finished. So this is your AND gate. Okay, so architecture body of the AND gate begin here. Then after you define process and then bracket process A comma B. So begin process begin here. Then your Y, no Y, yes, Y is here A and B. So AND gate is defined here. So then end the process. Okay, let me check this. Yes. Okay, so this is done. Now this AND gate also need to be defined as a component in the main program. Okay, so here component AND gate is end component. Okay, so this is done. Then let me say this OR gate check syntax whether it is correct or not. AND gate is OR gate is check syntax is going on. OR gate check syntax. Then by the mistake I make it B instead of BCD, I made it BSD. Okay, no problem, it is just the name. Okay, don't be confused, this is just the name only. I supposed to write it BCD, but I made it mistake BSD, but it is just the name, no problem. So here it is BSD only. Yes. Okay, check syntax successfully. Then OR gate. So AND gate also let me check for the AND gate. AND gate. Yes, AND gate check syntax going on. So this here AND gate check syntax is going on. Here I can write yes. So now the main BCD Adder behavior architecture will start here. So how much is your requirement? So this is your cell, let it be U1, then this is suppose U2, U3, U4, U5. Okay, so let me write. Okay, this is also successfully done. So U1, U2, U3, because U1, U2 already I have written. So what I need to write is the first one is parallel adder. So PA, I will make it parallel adder 1. Then next is your AND gate, 2 input AND gate. I will put it as A and 2 underscore 1. Okay. then one more, and 2_1, then or3 _1. Okay, then again PA parallel ladder 2. Okay, so these are the different things. So parallel ladder 1. So what is the name of the parallel ladder? It is parallel ladder only. So you just copy and paste because it should be exactly same. Okay, parallel ladder port map. Okay, I will come to this. Then AND gate port map. I'll finish it later. So then OR gate. So just copy and paste because it has to be same. The name has to be exactly same. So OR gate port map. And then sorry, this is also AND gate, no? This is only for okay. This is also AND gate. Okay, and finally this is parallel ladder again. Okay, now in the first parallel ladder, what are the input? As you see here, so in the first parallel ladder, inputs are A and B's. Okay, so A naught, B naught. Inputs are like this way. You need to define this parallel ladder A and B. Okay, so A naught, so inputs are A and B. So A naught, A1, A2, A3, B naught, B1, B2, B3. Then what else? The C in. Okay, directly C in. Then the output. What are the output? Here, so outputs are S0, S1, S2, S3. Okay, but this will be used as a signal because these are the output of the first 4-bit adder, and along with that, this goes as an input to others. Okay, so therefore I have to define signal here. Okay, so signal, what are the signals? So CS I cannot put because I was already used. So better I'll put it SS. Okay, SS0, SS1, SS2, SS3. Then your carry out. Okay, so carry out here I have considered as C out. So I can make it C3 as a signal. Okay, so from the first parallel ladder, all this will come as an output here. Okay, SS. So now what it is? This is SS0, SS1, SS2, SS3, and C3. Okay, that I have defined it as a signal. Now coming to the AND gate. Okay, so this is done. First parallel ladder is done. In the second AND gate. So what is there in the AND gate? In the first AND gate. Okay, in the first AND gate, SS3, because now it is signal SS3 and SS2, and output is again you have to define it as another signal. Let it be Y1. So here I am defining two more signals Y1, comma Y2. So here it is your SS3 and SS2. So SS3, then SS2 and Y1. Okay, so this AND gate is done. Then second AND gate, what comes in the second AND gate? The second AND gate, SS3 and SS1 and Y2. So SS3, SS1 and here Y2. Okay, so this AND gate is done. Then OR gate. What is the OR gate? OR gate is your C3, Y1, Y2, and the output here again you have to define another signal here. Suppose yn. Okay, so here I am defining one more signal yn, suppose. Okay, so in that input will be y1, y2, c3. So because c3 is the highest, this is c3, then output is yn. Okay, so this OR gate is also done. And then comes the last, your parallel adder. So now in this last parallel adder, what inputs? You see SS0, SS1, SS2, SS3 comes directly as an A input. Okay, so SS0, 1, 2, 3 comes directly here. Then the C in also 0, but the same C in here also it will be 0. But for modular structure, if you make it adder cum subtractor, then this will be 0, but this may not be 0 if you make it as this BCD adder cum subtractor. But for the timing it is just an adder. So since the same Cn will be goes here, so Cn will be here, that or you can put it as 0, binary 0 directly. Okay, then output. So what are the outputs here? Other input, B input. So B input here, B naught is 0. So B naught is again 0. Then your B1, this is B naught, this is B1, B2, B1, B2 is this Cn. Okay, so this yn I have considered. Okay, so it is yn, again yn, because this output, no. So then last one is again 0, binary 0 directly. So 1, 2, 3 input, 1, 2, 3, 4 input, 1, 2, 3, 4, then 1, 2, 3, that is seen. Just a minute, A, B, seen is will be at last. So this will go to the last. Okay, so these 4 are your A input, these 4 are your B input, this is your C input, Cn input. So input is done. Then finally the output. So what are the outputs? That's like A input, B input, C in, then as output. A input, B input, C in. Then output. Output is your directly this. So output is as it is given as output. So output will be your S0, S1, S2, S3, and finally carry out. Carry out is given as this C out. This is the BCD Adder. Okay, C out. C underscore out. This one. Okay, so it's done. Okay, let's save it. Now something is 63. Yes, the error is this. Yes, so the signal you have to define it as like a stereo logic. Yes, city logic. Okay, now so see, this is your BCD adder, under which this is parallel adder, under which these are the full adder, and get again another parallel adder is used, under which this full adder is adder. Okay, now let us check the syntax for the BCD adder. So syntax is going on. Then next, after this, what I need to do is apply the test bench for the BCD adder. Check syntax failed, something error.